What if I told you that scientists can only explain 5% of the entire universe? The rest, a staggering 95%, remains completely invisible to our instruments and defies our most advanced theories of physics. In this documentary, we're exploring the bizarre reality of dark matter and dark energy, cosmic components that shape our universe but remain utterly mysterious. Like trying to understand an entire ocean by examining a single drop of water, our current knowledge barely scratches the surface. We'll journey through cutting-edge discoveries and mind-bending theories that challenge our fundamental understanding of reality itself. The answers might be stranger than we ever imagined. The missing 95%. What if everything you can see in the night sky, all the stars, planets, and galaxies, makes up just 5% of what's actually out there? That beautiful spiral galaxy you've seen in photos, the stars twinkling above your home, the planets in our solar system, and even the atoms that make up your body, all of it combined represents just a tiny fraction of the total universe. When astronomers first came to this realization in the late 20th century, it shook the foundations of physics. Imagine the entire universe as an ocean. Everything we can see and detect directly, every star, planet, and galaxy, would amount to just a small cup of water from that ocean. The rest remains completely invisible to our instruments, detectable only through its gravitational effects. This wasn't a conclusion scientists reached lightly. The story begins with astronomers attempting to weigh the universe. They needed to determine how much matter exists in total, which turns out to be surprisingly difficult when you're dealing with something as vast as the cosmos. Scientists developed multiple independent methods to measure cosmic mass, and this is where things got strange. One approach involves studying how galaxies move within clusters. Galaxies aren't evenly distributed through space. They form groups in clusters held together by gravity. By measuring how fast these galaxies move, astronomers can calculate how much mass must be present to generate enough gravitational pull to keep everything together. It's similar to how we can determine Earth's mass by measuring the moon's orbit. Another method examines light from the early universe, the cosmic microwave background radiation. This ancient light carries imprints of how matter was distributed shortly after the Big Bang. By analyzing these patterns, scientists can determine how much matter existed then and track how it evolved into the universe we see today. A third technique involves gravitational lensing, when light from distant objects bends around massive structures like galaxy clusters. The amount of bending reveals the total mass causing the gravitational effect, similar to how magnifying glass bends light. What's remarkable is that all these different methods pointed to the same conclusion. There's far more mass in the universe than we can see. The calculations simply weren't adding up. The visible matter we can detect through telescopes, stars, gas clouds, planets, couldn't possibly generate enough gravitational force to explain what astronomers were observing. In the 1970s, astronomer Vera Rubin provided crucial evidence through her studies of galaxy rotation. She expected stars at the edges of galaxies to move more slowly than stars near the center, just like planets in our solar system. Mercury orbits much faster than Neptune. Instead, she found that stars throughout galaxies moved at roughly the same speed regardless of their distance from the center. This shouldn't be possible according to our understanding of gravity, unless there was substantial invisible mass distributed throughout each galaxy, providing extra gravitational pull. This discrepancy appeared everywhere astronomers looked, from small dwarf galaxies to enormous galaxy clusters. Something massive was missing from the equations. The same problem appeared when scientists studied the overall expansion of the universe. In the 1990s, astronomers discovered that the universe is accelerating in its expansion. This required some form of energy pushing everything apart, something completely different from the invisible mass holding galaxies together. Through decades of observations and calculations, scientists have now determined the universe's composition with remarkable precision. Ordinary matter, everything we can see and interact with, makes up just 5% of the cosmos. About 27% consists of dark matter, an invisible substance that interacts with normal matter only through gravity. The remaining 68%, the largest portion, is dark energy, a mysterious force driving the accelerating expansion of the universe. Dark matter doesn't emit, absorb, or reflect light, which makes it incredibly difficult to study. It doesn't interact with electromagnetic forces, yet it clumps together around galaxies in massive halos.
Without dark matter, galaxies,
they fly apart. They simply don't have enough visible mass to generate the gravitational force needed to hold themselves together. Scientists have proposed various candidates for what dark matter might be, from exotic subatomic particles to primordial black holes formed shortly after the Big Bang. Some have even suggested modifying our theories of gravity rather than introducing new invisible substances. Despite decades of searching with increasingly sophisticated detectors, we haven't directly observed a single dark matter particle. Dark energy presents an even greater puzzle. Unlike dark matter, which clusters around galaxies, dark energy appears uniformly throughout space. Its effects become more noticeable over vast cosmic distances. Some theories suggest dark energy might be an intrinsic property of space itself, that empty space contains inherent energy that drives expansion. Others propose more exotic explanations involving extra dimensions or modifications to Einstein's theory of gravity. The bizarre reality is that after centuries of astronomical observations and physics breakthroughs, scientists can only explain about 5% of the entire universe. We're like people trying to understand an iceberg by studying only the tiny portion visible above water. Understanding dark matter and dark energy could revolutionize physics, potentially leading to new technologies and a deeper understanding of how the universe began and how it might end. These invisible components have shaped the evolution of the cosmos from the earliest moments after the Big Bang, guiding the formation of galaxies and determining the ultimate fate of the universe. So what could possibly make up this missing cosmic mass? To answer that question, we need to examine one of the strangest discoveries in modern astronomy, the bizarre way galaxies rotate, seemingly breaking the fundamental laws of physics as we understand them. Galaxies that break physics. Why do galaxies spin as if they're breaking the fundamental laws of physics? According to everything we know about gravity and motion, galaxies shouldn't be able to rotate the way they do. Yet every galaxy we've examined reveals the same impossible pattern, a cosmic mystery that points to something massive hiding in plain sight. Let's start with how galaxy rotation should work according to Newton's laws of physics. Think about our own solar system. Mercury, the closest planet to the Sun, zips around its orbit at about 30 miles per second. Earth moves at a more modest 18 miles per second, and distant Neptune creeps along at just 3 miles per second. This pattern makes perfect sense. Objects farther from the center experience less gravitational pull and therefore move more slowly. This relationship is so reliable that we can use it to calculate the Sun's mass with remarkable precision. Galaxies should follow this same principle. Stars near the center of a galaxy should orbit rapidly around the galactic core, while stars at the outer edges should move much more slowly. Like dancers in a cosmic ballet, the performers closest to the center should twirl with dizzying speed, while those at the periphery should move in slower, more majestic arcs. If we graph the speed of stars versus their distance from the galactic center, we'd expect to see a clear downward curve, fast movement near the center, gradually decreasing as we move outward. This prediction comes directly from Newton's laws of gravity, which have been thoroughly tested and verified for centuries. But in the 1970s, astronomer Vera Rubin made a discovery that shocked the scientific community. Using a sophisticated spectrograph at the Kitt Peak National Observatory, Rubin studied the Andromeda Galaxy, our nearest large galactic neighbor. She measured how fast stars were moving at different distances from the galactic center by analyzing subtle shifts in their light spectrum, a technique called Doppler shifting. Stars moving toward us have their light compressed to slightly bluer wavelengths, while stars moving away have their light stretched to redder wavelengths. The amount of shift reveals the star's speed. What Rubin found defied all expectations. Stars at the outer edges of Andromeda were moving just as fast as stars near the center, sometimes even faster. This flat rotation curve appeared in galaxy after galaxy she studied. According to the visible mass of these galaxies, the outer stars should be moving much more slowly. Instead, they were whirling around at speeds that should literally fling them off into space. The conclusion was inescapable. Rubin later wrote in her notes, "The stars in the outer regions of galaxies were being influenced by matter we couldn't see." This revelation stunned astronomers, creating an immediate crisis in the field. Either Newton's laws of gravity were wrong, an extreme possibility given their success in explaining almost everything else in the universe, or galaxies contain vast amounts of invisible mass, extending far beyond their visible boundaries. The problem wasn't confined to a few unusual galaxies. Further studies revealed that virtually every galaxy demonstrated this same rotation pattern. Scientists began calling this missing component dark matter because it doesn't emit, absorb, or reflect light. Calculations showed that for most galaxies, The visible matter of stars, gas clouds, dust accounts for only about 10 to 20% of the total mass needed to explain their rotation. The remaining 80 to 90% must be invisible dark matter. Our own Milky Way galaxy appears to be embedded in a dark matter halo that extends far beyond the visible disk of stars, containing 5 to 10 times more mass than all the stars combined. Computer models suggest that dark matter forms roughly spherical halos around galaxies, extending much farther than the visible portions. The density of dark matter appears highest near galactic centers and gradually decreases outward. This extended distribution explains why stars at the outer edges of galaxies move so quickly. They're experiencing gravitational pull from a vast cloud of invisible matter surrounding the galaxy. Dark matter appears to form the backbone of cosmic structure. Computer simulations of the early universe show that dark matter clumped together first after the Big Bang, creating gravitational wells that attracted normal matter. Visible galaxies essentially form within these pre-existing dark matter structures, like cities built along invisible rivers. Scientists have mapped dark matter using a technique called gravitational lensing. When light from distant galaxies passes near massive objects, its path bends slightly due to gravity. By measuring these subtle distortions, astronomers can create maps of foreground mass, including invisible dark matter. These maps reveal vast webs of dark matter with galaxies nested within these invisible structures. Detailed studies of colliding galaxy clusters provide further evidence. When clusters collide, the normal matter, mostly hot gas, smashes together and slows down, while the dark matter halos pass through each other without interacting. The famous bullet cluster observation in 2006 showed exactly this pattern, providing compelling direct evidence for dark matter's existence. The rotation curves of galaxies tell us something profound about our universe. The stars and galaxies we see are just the visible tips of much larger structures. Without dark matter, galaxies would fly apart. The stars move too fast to be held together by the gravity of visible matter alone. Something invisible is holding our universe together. What makes this mystery particularly intriguing is that we can measure the effects of dark matter with remarkable precision. We can map its distribution, calculate its amount, and observe how it shapes galaxies and clusters. Yet we still have no idea what this mysterious substance actually is. It surrounds us, shapes our galaxy, and outnumbers visible matter 5 to 1, yet continues to evade direct detection despite decades of increasingly sophisticated experiments. The phantom substance. How can something make up 27% of the universe yet remain completely undetectable by all our instruments? This is the central paradox of dark matter, a substance that appears to be everywhere in the cosmos, yet nowhere to be found. It's like having an invisible guest at dinner who eats more than everyone else combined, but leaves no trace of their presence except for the missing food. Dark matter earned its name because it doesn't interact with light or electromagnetic forces, the primary ways we observe the universe. Stars shine, gas clouds emit radiation, black holes consume matter and release energy, but dark matter remains invisible. It neither emits, absorbs, nor reflects light, making it essentially invisible to our telescopes and detectors. As Nobel Prize-winning physicist Maria Spiro-Poulou once remarked, dark matter is the ultimate cosmic ghost. We know it's there from its gravitational fingerprints, but it refuses to show itself directly, challenging our fundamental understanding of physics. This creates a strange situation for astronomers. We can map dark matter's distribution with remarkable precision to its gravitational effects, yet we still have no idea what it actually is. Imagine being able to create detailed maps of ocean currents without ever knowing water exists. That's essentially the position scientists find themselves in with dark matter. What makes dark matter particularly unusual is how it interacts with the universe. Normal matter, the stuff that makes up stars, planets, and people, interacts through 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Dark matter appears to interact only through gravity, ignoring the other 3 forces. This selective interaction makes conventional detection methods ineffective, like trying to find a person who doesn't talk, doesn't leave, footprints, and walks through walls. And the only way you know they exist is because occasionally objects move as if someone had bumped into them. Scientists have developed several theories about dark matter's composition, with the leading candidate being WIMPs, weakly interacting massive particles. These hypothetical particles would have mass, explaining dark matter's gravitational effects, but would interact only weakly with normal matter. They would be fundamentally different from the particles in the standard model of physics, which describes all known particles like electrons, protons, and neutrinos. WIMPs are appealing because they would naturally form in the right amounts during the early universe. Calculations suggest they would have been produced in quantities that match the amount of dark matter we observe today. These particles would be all around us, passing through Earth constantly, yet interacting so rarely with normal matter that they remain invisible to our detectors. But WIMPs aren't the only possibility. Another candidate is Axions, extremely light particles originally proposed to solve a different problem in particle physics. Axions would be much lighter than WIMPs, but could exist in such enormous numbers that they would collectively contribute the mass we observe as dark matter. Under certain conditions, axions can convert to photons, which gives scientists a potential way to detect them. Some researchers propose sterile neutrinos as dark matter candidates. Regular neutrinos barely interact with normal matter. Trillions pass through your body every second without affect. Sterile neutrinos would interact even less, making them potential dark matter components. Primordial black holes, formed in the first moments after the Big Bang, represent another intriguing possibility. These ancient black holes could range from microscopic to planet size and would interact only through gravity, matching dark matter's observed properties. Recent gravitational wave detections have renewed interest in this possibility. Dark matter forms an intricate cosmic web spanning the entire observable universe. This web consists of dense filaments and nodes with vast empty voids between them. Normal matter flows along these dark matter structures, like water following channels in the landscape. Computer simulations reveal that this cosmic web formed early in the universe's history. Dark matter began clumping together earlier than normal matter, creating a framework that would later guide the formation of galaxies. These simulations show something remarkable. If you map only the dark matter in the universe and add visible matter later, following the laws of physics, you naturally get a universe that looks just like our own. The galaxies form where dark matter density is highest, clustering in patterns that match our observations. Without dark matter, these simulations fail completely. The resulting universe looks nothing like the one we see. Dark matter acted as a cosmic scaffold, providing the structural framework upon which the visible universe was built. Galaxies form where dark matter filaments crossed or within dark matter halos, like cities built at the intersections of invisible highways. We can now map this cosmic web through techniques like weak gravitational lensing. When light from distant galaxies passes through the cosmic web, its path bends slightly due to dark matter's gravitational effects. By measuring these subtle distortions across millions of galaxies, astronomers can reconstruct dark matter's three-dimensional distribution. What makes this cosmic mystery so profound is the scale involved. Dark matter constitutes about 27% of the universe's total energy content, more than 5 times as much as all normal matter combined. It forms the backbone of cosmic structure and plays a crucial role in galaxy formation. Yet despite decades of searching with sophisticated experiments, not a single dark matter particle has been directly detected. This absence of direct detection has led some scientists to question whether dark matter exists at all. Maybe our understanding of gravity needs revision instead. But the evidence for dark matter has only grown stronger over time, with multiple independent observations pointing to the same conclusion. There's far more mass in the universe than we can see. The hunt for dark matter. What happens when the world's most sophisticated detection equipment keeps coming up empty-handed? This is the frustrating reality facing scientists hunting for dark matter. Despite building increasingly sensitive detectors, positioning them in the most remote locations on Earth, and spending decades searching, researchers have yet to conclusively detect a single dark matter particle. The search for dark matter represents one of the largest coordinated scientific efforts in history. Research teams across the globe have designed experiments costing hundreds of millions of dollars, yet this mysterious substance continues to evade direct detection. Finding something that barely interacts with normal matter requires extraordinary measures. One of the biggest challenges is filtering out false signals. Earth is constantly bombarded by cosmic rays, radiation, and particles that could be mistaken for dark matter interactions. To solve this problem, scientists have created the quietest detection environments possible. Many dark matter detectors operate deep underground, sometimes more than a mile beneath the surface. The rock above shields the detectors from cosmic rays. The Gran Sasso National Laboratory in Italy sits under a mountain with 1,400 meters of rock overhead, providing natural protection from unwanted signals. In these silent underground chambers, researchers wait patiently for the faintest whispers from the cosmos. The detectors run continuously for years. Scientists monitor data streams, hoping for that elusive signal that might finally reveal dark matter's presence. The silence grows more deafening with each passing year. Even underground, natural radioactivity creates noise in the detectors. Scientists address this by constructing massive tanks filled with ultra-pure materials like xenon, argon, or germanium crystals. These detection chambers are surrounded by carefully selected materials with minimal radioactive contamination. Some experiments use water shields, enormous tanks containing thousands of gallons of ultra-pure water to absorb stray radiation. The detection principles, while varied, share common elements. When a dark matter particle strikes an atom in the detector, it should produce measurable effects: a tiny flash of light, a few freed electrons, or a minute temperature increase. Sophisticated sensors capture these faint signals. The xenon experiment, buried deep under the Grand Sasso Mountain, contains thousands of kilograms of liquid xenon cooled to minus 95 degrees Celsius. Its sensors can detect even a single photon of light. The Lux Zeppelin experiment, nearly a mile underground in a former gold mine, holds 7 tons of liquid xenon surrounded by 70,000 gallons of water. Other detectors, like CDMS, use crystals cooled to nearly absolute zero temperature. Despite their remarkable sensitivity, these detectors remain silent. No experiment has produced a definitive dark matter detection confirmed by others. The Dama Libra experiment has detected intriguing seasonal variations for over 20 years, but other more sensitive experiments haven't confirmed these findings.